Hi, Wade Hampton, Honors Chemistry students. In today's lesson, we're going to be talking about the relationship between wavelength, frequency, and energy of visible light and other forms of electromagnetic radiation. Now, there's two really important equations that deal with the math that's related to electromagnetic radiation and the wavelength and frequency and energy. And that's E equals h nu and C equals lambda nu. Let's take a quick look at what each variable in this equation stands for. The E in this first equation stands for the energy per photon. So this is how much energy a single photon of whatever color of visible light you happen to be looking at. It could also be the energy per photon of other forms of electromagnetic radiation, like a radio wave or an X-ray or something like that. Energy is measured in joules, so this is the unit that should be used for energy. H in this equation is a constant. This is Planck's constant. Now, constants by definition don't change. This is always the same number. So I've got this written out next to the equation. H is 6.626 times 10 to the negative 34th joule seconds. And this is just a number that you're probably not going to be given in mathematical problems relating to this. So you just need to know that, hey, if you need to use that H, that's always going to be the same number. It's that 6.626 times 10 to the negative 34th power. All right, and then the final variable in this equation, this funny-looking V here, is actually nu. When I say nu, I mean like N-U, the Greek letter nu. And in this equation, nu stands for the frequency. Now, frequency is just the number of wave cycles that pass by a fixed point per second. So you could use a unit of 1/seconds, but most often that is substituted for the unit hertz, which can be abbreviated Hz. Okay? In the second equation here, we've got a C, and C stands for the constant speed of light. Speed of light's not dependent on color. Every color moves the same speed through a vacuum, through empty space. Now, that's not necessarily true if it's moving through water or glass or something like that, but every color of light moves at this 3 times 10 to the 8th meters per second. Now, if you were to turn this back into a regular number, this would be about 300 million meters per second. So that's pretty fast. All right. The funny-looking upside-down Y here in this equation is actually a Greek letter lambda. And this lambda in the equation represents the wavelength of light. Now, because this is just a length and we're working in the metric system, this length is going to be expressed in regular old meters. Okay? And it's very important that if you substitute a wavelength into this equation, you make sure that that length is in meters, or else it's not going to match with the meters portion of the speed of light constant that we have here. So the units of length in the speed and in the wavelength need to match each other. Now, most of the time, if you're working with visible light, wavelengths are in nanometers. Now, nanometers, the prefix nano means 1/billionth. If you were to put that into kind of scientific notation, a billionth is 10 to the negative 9th power. That's 0.00, lots of zeros before you get to that first one. And so if you were given, say, a wavelength like 400 nanometers, which would be some violet light, and you wanted to turn that into regular meters, you could do that a couple of different ways. One would be that you could just substitute the prefix nano for this times 10 to the negative 9th power. So you could say this is the same thing as 400 times 10 to the negative 9th. Now, we got rid of the nano and replaced it with times 10 to the negative 9th. So now this is just regular meters. But this is improper scientific notation. Proper scientific notation would look like this: 4 times 10 to the negative 7th meters. All these three are the same size. Okay, they're the same. They're the same distance. The reason that this number could look like this is because if you were to put this in proper scientific notation by moving the decimal 2 places to the left, so that you only had one non-zero digit to the left of the decimal, then that makes the 400 100 times smaller, and so the times 10 to the power placeholder would have to be 100 times bigger to compensate, and that would turn times 10 to the negative ninth into times 10 to the negative seventh. Okay, so your calculator will often spit out numbers that look something like that. So if you saw 4e to the negative seventh power for a wavelength in your calculator, like this, 4e negative seventh, that many meters would be the same thing as 400 nanometers. Okay? All right, now let's work a couple of problems that are going to help us to kind of reinforce our understanding of this and make sure that we can do the math in the calculator and things like that. All right, so I've got my equations here and my constants, and I've also got a handy chart here that shows different colors of light and wavelengths for each of those colors of light. In this first example, it says, what color of light has a frequency of 4.84 times 10 to the 14th hertz? Okay, now this is a frequency. Now remember, frequency is the nu in the equation. So this is giving me a nu. It's asking me for a color, so it's not really asking me for a number, but if I'm going to use this color chart up here, I'm going to need a wavelength. So really, I need to find the lambda. I need to find the wavelength to be able to answer this question so that I can compare that wavelength with the color chart to figure out what color I'm talking about. Okay? All right, so if you start off with the equation that has both of these things in it, that's the C equals lambda nu equation. The speed of light equals frequency times wavelength. So this is the equation we're going to be using, C equals lambda nu. Okay? Now, I want to find the wavelength in this equation. So I need to get this lambda by itself. The easiest way to do that is just to divide the frequency to the other side, or divide both sides of the equation by the frequency. And if you do that and rearrange the equation, then it would appear this way. The wavelength would be equal to the speed of light divided by the frequency, or lambda equals c over nu. Okay? All right, so all I would need to do then is make substitutions and divide these two numbers to figure out what the wavelength would be. I know the c is always the same number. C is equal to 3.00 times 10 to the 8th meters per second. And the lambda, the nu is given to me in this problem. So I've got the 4.184, or 4.84, rather, times 10 to the 14th power. Okay, so I just need to divide those two numbers. Let's go to our calculator and see what that would look like. Okay, all right, now it's important that if you're dividing numbers in scientific notation that you put parentheses around them, because your calculator, or at least most calculators, aren't too smart about making sure that they divide by the entire number. Your calculator follows, unfortunately, order of operations all too well. So you have to make sure that your calculator understands that it needs to divide by this entire number and not just a portion of it. So I think I would enter it into the calculator something like this. 3, you don't necessarily have to put these zeros on here. So 3 times 10 raised to the 8th power. Go ahead and close that off. Divided by, and open another set of parentheses for my denominator here, 4.84 times 10 raised to the 14th power. Okay? And voila, the calculator spits out 6.19 blah, 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 e negative 7. Now, it's very important that you understand that this e negative 7 means times 10 to the negative 7th power. So, we're going to have this 6.17 times 10 to the negative 7th. Now, when you solve for a length, a wavelength in this equation, it's going to be in the standard unit of length, which is in meters. And unfortunately, our color chart up here is in nanometers. So we would need to change this number back into nanometers to be able to compare it to that chart. But that's not too hard, okay? If nanos times 10 to the negative ninth, so if we made this, 10 to the negative ninth, which is 100 times smaller, then this would have to be 100 times bigger, which would be 617. Not 600 or 6.17. So if we had 617 times 10 to the negative ninth meters, this would be 617 nanometers. Okay, 617 nanometers. Looks like it's going to be somewhere in between the 600 and the 650 up here. Estimating we're probably looking at some color of yellow light in this case. Okay, final answer. We're looking at yellow light. Okay. All right, and our second example here, this says, what is the energy per photon of red light that has a wavelength of 700 nanometers? Okay, now this time it's asking me for an energy. All right, so I'm looking for this guy. I want to know what the energy is. Now to be able to get that energy equals the Planck's constant times the frequency. And I'm reading this question, and I don't see a frequency anywhere in there. What I do see is a wavelength. Okay, so this may actually be a two-step problem where we actually have to use both equations. My plan is that I'm going to use the C equals lambda nu equation to find a frequency. I'm going to do this first, and then once I know what that frequency is, I'll have that frequency that I can plug into this other equation so that I can ultimately find that energy, find that E. Okay? All right, so again, let's start with our C equals lambda nu here equation. So if C equals lambda nu, which thing am I trying to get by itself? Oh, I need this nu. I need the frequency by itself. So to get this by itself, I'm going to divide the lambda to the other side. That's going to make the equation look like this. Nu equals C over lambda. Now the C was 3.0 times 10 to the 8th power meters per second. We know that's a constant, right? The lambda, we got to be careful before we plug this in because this original lambda was in nanometers, so we just need to change this into regular meters. You could call this 700 times 10 to the negative ninth meters, or 7 times 10 to the negative 7th meters. Probably it's just easier to say, let's just substitute times 10 to the negative ninth for the nano. So 700 times 10 to the negative ninth is going to be our lambda there. Okay? All right, and we just need to divide those two numbers to figure out what the frequency is. Okay, so we'll go back to our calculator here. All right, so this time I'm going to do 3 times 10 raised to the 8th power, and I'm going to divide that by 700, and this is 700 nanometers, so 700 times 10 raised to the negative 9th meters. Okay, and my calculator spits out 4.29 times 10 to the negative 14th power. Okay. Okay, so I got an answer for my nu. Now, I still haven't completely solved the problem yet. I know what this is now, but I need to finish this problem by finding the energy. So to actually take this, from here to here, I need to go back to the other equation now. So energy is going to be equal to h nu, or Planck's constant, times the frequency. And you know what? I've already got the frequency, and it's in my calculator. I'm not going to reinvent the wheel here. I'm just going to take the same answer that I just got, which was this, and just multiply it by Planck's constant. So if I just take that answer and multiply by 6.626 times 10 raised to the negative 34th power, okay, that's Planck's constant, then I should be able to get my energy. So the energy here looks like 2.84 times 10 to the negative 19th power. That's common for visible light, to have powers on the order of 10 to the negative 19th joules. Okay, remember the unit here is joules since we're talking about energy. Okay. All right, so here was a wavelength frequency problem. Here was a problem that actually used both equations and related all three variables, the frequency, the wavelength, and the energy. Okay, hopefully that was helpful for you in terms of understanding how to deal with calculations relating to the energy, frequency, and wavelength of visible light. Until next time.